Hey, EP Statistics, welcome to section 11.2. We're continuing with chi-square distributions. We're going to look at inference for two-way tables. So we're no longer just going to be looking at like one distribution of proportions. We're going to be looking at two or more potentially, and the setting it depends. So by the end of this section, you should be able to state appropriate hypotheses and compute the expected counts in chi-square test statistic for a chi-square test based on a two-way data in a two-way table. You should be able to state and check the random 10% and large counts conditions for a chi-square test based on data in a two-way table, calculate the degrees of freedom and p-value for a chi-square test for the two-way table, perform a chi-square test of homogeneity, perform a chi-square test of independence, so two different types of tests that are very, very similar, and choose the appropriate chi-square test in a given setting. So start out with an example here. Does background music influence what customers buy? One experiment in a European restaurant compared three randomly assigned treatments: no music, French accordion music, and Italian string music. Under each condition, the researchers recorded the number of customers who ordered Italian and other entrees. So our null hypothesis is that there is no difference in the true distribution of entrees ordered at this restaurant when no music, French accordion music, or Italian string music is played. And our alternative hypothesis is there is a difference in the true distribution of entrees ordered at this restaurant when no music, French accordion music, or Italian string music is played. Note that the alternative hypothesis does not state that each distribution is different, just that they're not all the same. Maybe just one is different. All right, it's going to help to look at some data to see what we're talking about. So in this case, we're looking at the type of music played. This was kind of the treatment, kind of our control here, I guess, and then French music being played and Italian music being played, and then what was ordered. And so we're interested in, is this distribution the same as this distribution, the same as this distribution? Now, this is just a sample of data. So ultimately, we're trying to infer about the population. If we had done this, for individuals like these in the study, if we had done no music, what type of, what would their distribution have been, and so on. So we can observe, here our observed values are percents. So to figure this out, we've got, when no music was being played, we've got 30 something percent. So 30 out of 84, whatever that is, it's some 30 something percent. And then Italian was 11 out of 84, that proportion ordered Italian, and 43 out of 84, which is a little over half, ended up being other. And then when French music was played, we had that same similar distribution, not very likely to order Italian when French music was played, only 1 out of 75, so whatever that percentage is, and so on. And when Italian was played, it seems like, we had these percentages. So these are sample, or really, I guess, treatment percentages, since it's kind of an experimental design. Are they significantly different? So we see, across the board, Italian was ordered less, but, was it a little less likely if there, and so on. Is that a significant, or could that just be, the result of random assignment? So do the differences in these data distributions provide convincing evidence that background music affects customer behavior at this restaurant? Or is it plausible that the background music has no effect on customer behavior, and that these differences are due to the chance involved in the random assignment of treatments? So we could compare many pairs of proportions, ending up with many tests and many p-values, but this is a bad idea. So I could see, is the proportion here different than this one? P1 minus P2, we could see it, do a two proportion z-test here, or this proportion to that one, or compare this one to that one, or, we could do a whole bunch of significance tests. The problem is we're going to be doing multiple tests. So performing multiple tests on the same data increases the probability that we make a type 1 error on at least one of the tests. If we do a whole bunch of tests, you're going to get that false positive, just by chance, 5% of the time. So you run 20 tests, you're going to expect one, even if there is no difference. So the problem of how to do many comparisons at once without increasing the overall probability of a type 1 error is common in statistics. So statistical methods for dealing with multiple comparisons usually have 2 steps. Perform an overall test to see if there's convincing evidence of any differences among the parameters that we want to compare. And then, when the overall test shows there is convincing evidence of a difference, perform a detailed follow-up analysis to decide which of the parameters differ and to estimate how large the differences are. So we want to perform that overall test to see if they're different. In order to do this, we need to figure out what would have been expected. To find the expected counts, we start by assuming that the null hypothesis is true, and in this case, that they're all the same. That this distribution is the same as that distribution, and that's the same as that distribution. We won't have in this case specific numbers given, where like the last section we said, oh, the first P1 is this, and P2 is that, and P3 is that, and so on. We're not going to be given those numbers. So in this case, we're going to have to come up with it kind of based on our data. So if the specific type of music that's playing has no effect on entree orders, the proportion of French entrees ordered under each music condition should be the same. So if overall we saw 99 out of 243, so 40%. That's kind of actually like if we had pooled all these proportions together. We got 99 out of 243, which is about 40%. So we would expect all of these to be 40% of the entrees ordered. But then, if we think about, all right, so no music was played for 84 of those, so we take that proportion, that 99 out of 243, and multiply that 40%, times 84, that's what we would expect this number to be. So we observed 30 in this category. We would expect overall 99 out of 2, that proportion times this many gives us 34.22. And that's what our expected would have been for this cell alone. We call these cells in this table. And then we move over to the next cell, and we could do the same thing. We could do the same fraction, this total here over the grand total, so that's the proportion, times the 75, the total for that column, and get this. And so we end up getting this way of calculating expected counts by doing, and this is for our chi-square test that use two-way tables, both our test of homogeneity and our test of independence. We'll get to those. They both use this way. You do your row total times your column total divided by your table total. That's the math of what we just did. We thought of it as like row total divided by table total times column total, but you get the same thing. And you could also do another thing here. You could do the column total divided by this times that, and you get those proportions, what proportion we're in this group, and then that's what proportion of 99 we'd expect. Either way, this works out. Row total times column total divided by table total. And so here we've got our expected counts. So our expected counts, take the row total times column total divided by table total. As with chi-square tests of goodness of fit, the expected counts should not be rounded to their nearest whole number. While an observed count of entries ordered must be a whole number, an expected count need not be a whole number. The expected count gives the average number of entrees ordered if the null hypothesis is true and the random assignment process is repeated many times. So that's what we mean by expected. It's not like what should have occurred. It's just what long-term, on average, what we would get. So then we get our chi-square test statistic. The good news is this is the exact same thing. Observed minus expected squared over expected. You just got to do it for multiple rows and columns now. So the sum is over all cells, not including the totals, so the actual data in the two-way table. And so in that example, we would have had the 30 minus 34.22 squared over 34.22. And then the next category, we had 39. I'll go back and show you where we were at. So that's where our expected, the 30.56, but our original data was 39. So there's 39 minus the 30.56, and so on. And so we do that across the rows, and down the rows to get all of those, all the way to our very last one. And then we get a chi-square test statistic by summing up those components. And there we have 18.28. And so that's a thing that measures how far what we observed is from what we expected, and compiles it all into just one nice little test statistic number. In the do steps, you aren't required to show every term in the chi-square test statistic. Writing the first few terms of the sum followed by a ... is considered showing work. We suggest that you do this and let your calculator tackle the computations. That's fine. I think that's a good way of doing it. Technically, you can also get away with just even not showing that, but that can be risky. But yeah, here is our, your chi-squares definitely needs to be in there. All right, so example problem. For a class project, Abby and Mia wanted to know if the gender of an interviewer could affect the responses to a survey question. The subjects in their experiment were 100 males from their school. Half of the males were randomly assigned to be asked, would you vote for a female president? By a female interviewer. The other half of the males were asked the same question, would you vote for a female president, by a male interviewer. A table shows the results. So state the appropriate null and alternative hypothesis, and then show the calculation of the chi-square and so on. All right, so the first one, the appropriate null hypothesis, is that the whole null hypothesis is no difference or no change. It equals something. So in this case, there's no difference. There is no difference in the true distribution of response to this question when asked by a male interviewer and when asked by a female interviewer for subjects like these. So again, we're saying that when they were asked, this distribution is the same as that distribution, and of course not in the actual sample data, but for the population, that the gender of the interviewer didn't matter. These are the same. So we're comparing those. Yeah, these columns are the same. You could also set this up so that the rows are the same. The two-way table could be flipped and so on. So don't always expect it to be columns being the same. In this case, that's what we're looking at. The alternative hypothesis is there is a difference in the true distribution of the response to this question when asked by a male interviewer and when asked by a female interviewer for subjects like these. All right, so part B, show the calculation for the expected count in the male/yes cell, then provide a complete table of expected counts. So male/yes, we would do row total, 69, times column total, 50, divided by table total, 100. And that will give us our expected count, and we can kind of go through and fill that all out. So 69 times 50 over 100 gives us 34.5. We observed 30, we would have expected 34.5. You could do that for all of these. You could do 69 times 50 over 100 to get this 34.5. And then 11 times 50 over 100 gives us that, and so on. So then they want us to calculate the value of the chi-square test statistic. Basically, it's this number minus that number squared over that number. This number minus 30, so 39 minus 34.5 squared over 34.5. And then you don't do the totals. 8 minus 5.5 squared over, and so on. So we can do that all the way through that last one, 8 minus 10 squared over 10, and get that chi-square test statistic. All right, so we've got some conditions that we'll do with these inference procedures as well. And this is the test of homogeneity. It's slightly different for the test of independence. So the data come from independent random samples or from groups of a randomized experiment. So we're seeing if multiple groups are the same, homogeneous across the groups. So that's what we're looking for, to see if two or more distributions are the same, not necessarily just two. The 10% rule, when we're sampling without replacement, that needs to be there, and then all expected counts are at least 5. So pretty much the same, only with the test of goodness of fit, it was just one random sample, and we're seeing if it fits some given distribution. Now we might have 2 or more random samples. Or randomized treatments, and similar to like our 2-sample procedures. So example problem, we're going to check conditions and work on this one. So in the preceding example, you read about an experiment to determine if the gender of the interviewer affects responses to the question, would you vote for a female president? Here are tables showing the observed and expected counts. So our observed counts are over here. Here's what we would expect if there was no difference. And notice that in this case, those numbers are identical. That's because we had the same totals. But if these numbers were different totals, we could actually have different expected counts between these, just relative to the size. They'd be the same proportions, but they wouldn't be the same exact number. In this case, they are the same number because we got 50 male, 50 females. So that's what we would expect. So we calculated that chi-square test statistic. Verify that the conditions for inference are met. So we want to have our random condition met. So they were randomly assigned a treatment. So the treatments were randomly assigned. Check. The large counts condition is met, and so all expected cell counts are at least 5. We can look at the expected table up here. All of those are at least 5. The no category, just a little bit. And then note that they didn't check the 10% condition because Abby and Mia didn't randomly select subjects from some population. They randomly assigned treatments from a group of volunteers, so it wasn't a sampling without replacement, so you do not need to check that condition. So part B was use table C to find the p-value, then use your calculator's chi-square CDF command. So our degrees of freedom, one second. All right, sorry, I was looking back to see if I missed it. I thought I might have missed the slide on it. But yeah, degrees of freedom for this is actually rows minus 1 times columns minus 1. And that's kind of a bit weird. If you had, like, for instance, the totals and some cells were missing, you could figure out what they were. So for instance, this cell, if this 39 was missing, I could figure it out from, the sum being 69, and I could actually do that for several of these. And so actually the number that are free to vary, if I actually know in this case any two, we could figure almost any two. There are two that could vary, and then I could actually figure out the rest through, like, if I knew these two, I could add them up to figure out this one, and then add a horizontally across and do that one. So it's actually rows minus 1 times columns minus 1, and I thought that they would have said that already. But so here's what we actually use here. Our degrees of freedom in this case is 3 rows minus 1, so it's 2, times columns minus 1, which is 1, and so we end up 2 times 1, which is 2. For our degrees of freedom. So that is degrees of freedom for the test of homogeneity as well as the test of independence. Using our table, we could get an estimate for it. That was our chi-square. We could look at 2 degrees of freedom, or we can use technology. So we could do chi-square CDF from 4.25 up to infinity with 2 degrees of freedom and get that 0.119, which is not, small enough to be significant. So interpret the p-value from the calculator. So assuming the null hypothesis is true, that's always how our p-value interpretation should start. Assuming that the gender of the interviewer doesn't affect the response to this question, there is a 11 to 12% chance, 11.9% probability of observing differences in the distributions of responses as large or larger than those in this study by chance alone. So there's 11% chance. It's not going to be quite enough to convince us. So what conclusion would you draw? Because our p-value is greater than an alpha level of 5%, we fail to reject the null hypothesis. There is not convincing evidence of a difference in the true distribution of responses to this question when asked by the male interviewer and when asked by a female interviewer for subjects like these. It's not concluding that they're the same. We just did not find significant evidence that they are different. We may have made a type 2 error in this case. So as usual, though, in this, you can do that stuff by hand. Technology saves us time and gets the arithmetic right. So this one's a little bit weirder. To enter these values into your calculator, you're actually going to have to put them in a matrix. So let me show you real quick how to get to that. You're going to want to get to where you have a matrix just like this. So let me show you on the calculator. All right, so on your calculator, matrix is above the x to the -1 button. You're going to hit second, and then where it says light blue matrix or whatever color it is on your calculator, x to the -1, and that's going to bring you into your matrix screen. And you may have stuff in here from before. It may not, may not have anything in there. If you want to clear them out, I can show you through the memory, but you don't need to. So what I want to do is actually need to enter in a matrix for this data, and it's a 3x3 matrix is what they're trying to do here. Let me make sure hold on one second. So the example that they're giving in this problem, they're actually going back to this original data. So that's the 3x3 matrix that they're entering. So that's what I'll be putting in right here when I type this in. So once you get into matrix, you're going to want to edit, and you're going to type that in. So I'm going to go matrix over to edit, and then I'm going to choose to make this a 3x3 matrix, and you'll notice that the spaces get bigger. And then to fill this in, I'm going to be typing in the numbers they had here, which were 30, 39, it just goes across the rows, 30, 11, 1, 19, 43, 35, and 35. And so this was the French, Italian music, no music, so on and so on, seeing if they're the same. All right, so then the next step is we go to chi-square test. This is not chi-square goodness of fit test, this is chi-square test. So we're going to go in. Once I have that matrix in, and it should show it if I go to matrix, it's now a 3x3, and I could enter and see what it is. But we're going to go to stat tests, and we're going to go to chi-square test. Not goodness of fit, but the actual chi-square test. And what's great about this, it asks for an observed. It asks expected, but it actually I don't need to type in the expected. This program is really nice because what it's just going to do is it's actually going to calculate the expected for me, and this is kind of where is it going to store it. It's going to put it into matrix B. Don't really care about the color unless we're drawing and we care about color. We can calculate this. It's going to calculate my chi-square test statistic immediately and give the corresponding p-value. So you'll see that this matches what they give over here. That's the chi-square test statistic and p-value that they got, so that'll match ours. It calculates the degrees of freedom. In that case, it was our 3 by 3, so it's 2 times 2, so it's rows minus 1 times columns minus 1. So it gives us that appropriate chi-square, and it'll actually even give us that expected counts in matrix B. So if I come back over here and show you that, oops, oh, there's my Hoth battle background. The p-value was really, really tiny on this one, the degrees of freedom 4. But what's really cool is when we go into matrix, it actually adjusted this matrix B. I had it as a 2 by 2 before. And I could tap over here to edit B to see what it is and see those numbers. Those are all of our expected counts. We could also do this by just typing in matrix B and having it display on our screen and observing what all of our expected were. And so it does all that math for you. Very nice to have that. So, AP exam tip, you can use your calculator to carry out the mechanics of a significance test on the AP statistics exam, but there's risk involved. If you just give the calculator answer without showing work and one or more of your entries is incorrect, you will likely get no credit for the due step. We recommend writing out the first few terms of the chi-square calculation followed by ... This approach may help you earn partial credit if you enter a number incorrectly. Be sure to name the procedure chi-square test for homogeneity and to report the test statistic chi-square equals 18.279 and degrees of freedom 4 and p-value of 0.01 to make sure you get all that stuff that's on your computer spit out.